think it was, that hovered off the coast of North Carolina. Most of you are too young for it. Andre, I believe you were born before '99.
Yes.
Do you remember the name of the hurricane that that hung off the coast of North Carolina and stayed there for a bit?
Oh my God, I don't.
Okay. I was thinking it was Hurricane Floyd, but I could be wrong on that one. We'll call it Floyd anyway. Floyd got off the coast of North Carolina and hit the way the air pressure was working as it basically stalled, and it was still hurricane force and a lot of flooding. So my brother posted on Facebook, the coast is getting hit by a ton of rain. And so I thought, wait a second, how much is a ton of rain? So let's figure it out. 1 ton of rain, that's 2,000 pounds. Of course, we're cool, so we're going to use metric here, so I need to figure out how many newtons that is. So I just go to the handy dandy book near the back, and under force, 1 pound is 4.448 newtons. 1 pound, 4.448 newtons. So I'm going to multiply by 4.448 newtons per pound. Pounds will cancel out. And I'm left with how many newtons is a ton of rain?
$8,896
8,896. We got,
newtons.
yep. Newtons, yes. Anyone else?
I didn't say anything.
Okay. Anyone else got the same number? Okay. All right, so that's the weight of a ton of rain in newtons. Let's figure out what the mass is. How would we find the mass?
F equals MA.
Okay, that we have a just slightly shorter route.
Could you do weight equals M times G?
Yeah, mg, which comes from F equals ma. So we're trying to find m. So what would you do?
Divide by 9.8.
Yep, all right, so 8.896 newtons over 9.8 meters per second squared.
Minus 7.75.
907.75 units.
Is it newtons, meters?
Are you trying to do it from the units here?
Yeah.
All right, so if we're gonna do it from the units there, we have newtons divided by meters per second squared. So that's a newton divided by meter per second squared. Fraction bar is just division. And dividing by a fraction, it's the same as multiplying by the reciprocal, so that's a newton times second squared per meter, which would be a newton second squared per meter. That is a legitimate unit. However, what's the short version?
I'm forgetting, the weight, right? What are we?
It's a mass.
Mass? Kg. Which is kg, yeah?
Say-
Kg?
Yeah, kilogram.
Yeah.
Kilogram. That's a kilogram right there. So we have 907.75 kilograms of water being dumped on the coast of North Carolina, according to my brother. Let's figure out what the volume is. The density of water. Another one of those cases where the density of water, at least the approximation is, because water is universal, they came up with a system where it was equal to 1, because it's just an easy number to work with. And it's 1 gram per cubic centimeter. Now, I have my mass here in kilograms, so I can do one of two things. I can get that in terms of kilograms, or get this in terms of grams. Well, or we could just look up what the textbook says. Textbook does not give it to us in grams per cubic centimeter, that's just historically, that's what, actually, there's some science disciplines that still use grams per cubic centimeter, but this is also 1,000 kilograms per cubic meter. And that's equal to the mass of 907.75 kilograms divided by the volume. The math problem we're working with here is I have 1,000, is equal to 907.75 divided by V. That's the math problem we're working. So what is the volume of a ton of rain?
It would have to be 907.75. No, it wouldn't. Never mind.
0.90775 units.
Meters? Cube.
Yeah. Meters is the length, so volume cubed. All right. So let's see, we have, set up our cubic meter here. So that's 1 square meter. Cubic meter, we add a third dimension. So imagine a box that basically is this tall, that wide, this deep. That's a cubic meter. So 0.907 means that the box fills up to about here. So I respectfully responded to my brother. And I said, that's about 3 bathtubs full. I guess they're getting a light misting. But I posted it with brotherly love. All right. When dealing with fluids, when I use the term fluid, I mean a gas or liquid. Finding the exact force that it exerts becomes more difficult. When you start dealing with things that aren't sort of connected. There are times when it's convenient, but times when it's not. This is when we start getting into pressure. And so pressure is the force that it applies divided by area. So imagine I have a container here filled with water. International symbol for filled with water. And I stick a small cube of something in the bottom of it. If you've ever been to the bottom of a swimming pool, at least at some age I started really feeling my ears and it started to hurt, but as a kid it didn't. But you definitely feel pressure the farther down you go. And the pressure comes from the fact that there's a weight above you. All this water that is above this cube right here is pressing down on it. And so the force being applied, or the force being applied down here, is equal to the weight of the water above. Weight of water above. And weight is just mg. And mass, go back to density, density is mass divided by volume. Mass is just density times volume. That is bad notation there, let's try that again. Mass equals density times volume. And so the weight of the water, I can just take the density of water times the volume of the water times G. So rho VG shows up in a bunch of equations. The question in this situation, what's the volume? Because ultimately I'm trying to find the pressure that's exerted on this cube here. So suppose I have a really tall rectangle box. If this is Amazon, the size box that they would send to, pack a gum in. What's the volume?
The length, the width, and the height, all multiplied together.
All right, do you care which one is which?
No.
Okay.
They're all getting multiplied.
Say it again?
It's all getting multiplied together.
Absolutely. All right, so length, width, and height, typically length, people make the longest side, but it doesn't have to be. So I'm just gonna do length, width, height. In this particular case, my cube here would have to be, this would be length, and this would be width. So my volume in this case is rho, length, width, height, times G. That's just my volume right there. So now let's figure out the pressure that this water is exerting on it. So pressure is the force, which is just the weight of that water, which is rho times length, width, height, G, divided by the area that is pressing on. Well, how do you find the area of that top of that cube? Sorry, just say it.
It'd be the length and the width.
Yeah, it's just length times width.
Yeah.
Length cancels out, width cancels out, and I'm left with rho hg, or as it's usually written, rho gh. So this is the pressure in a fluid at a depth of h. Let's actually stick some numbers on this thing. So those cubes that some of you are using were 3 centimeters by 3 centimeters by 3 centimeters. So 3 centimeters by 3 centimeters by 3 centimeters. That would be the, I saw some around here somewhere. Where are any of those cubes? I hope you just remember what they look like. Okay. Oh, there's one. All right, so roughly 3 centimeter by 3 centimeter by 3 centimeter. Stick it in a bucket of water. And let's say the top of this cube is 0.7 meters down. It's a big container. What is the pressure being exerted on top of it? Well, it's a plug and chug. Density of the water, So 1,000 kilograms per square meter, per cubic meter, times the height, 0.7 meters, times G, 9.8 meters per second squared.
Six, oh, blah, 6,860. I'm not sure.
6,860.
I don't know what the units would be.
Anyone want to take a shot at the units?
You're trying to get it in pressure?
Yes, it's a
It's
formula for pressure.
not PSI, is it? But
This would not be PSI. PSI is a unit of pressure, but not in this case.
It would make sense that it's like kilograms per square meter or something, right?
Why would that make sense?
Or, cause it's just the metric version of PSI.
Yeah, but kilogram is not the metric equivalent or analog of pound.
Does it have newtons in
Quite possibly.
it?
It's force divided by area. So newtons per
Meter,
meter is one-dimensional. Area is two-dimensional.
Meter squared.
Yes. Newtons per square meter. Now, in this particular case, it's 1 square centimeter, so it's not experiencing a whole lot of weight coming from the water. I mean, 1 square meter, again, picture that, that's a lot of water sitting on top of it. Now, this unit here of newtons per square meter apparently is too much for physicists to write, because they came up with a shorthand for that one. It is known as the Pascal. I guess the unit's not capitalized. Pascal. And so Pascal is just by definition a newton per square meter.
I'll send you a picture.
Hi.
It's still running. Don't know what juices are. Oops, 17%. Alright. Excuse me. Thus the physics joke of Newton, Heisenberg, and Pascal are playing hide and seek. Heisenberg is closing his eyes, counts out, and Pascal goes out and runs hide somewhere. Newton stands right behind Heisenberg. Puts out a 1 meter by 1 meter square and stands in it. Heisenberg turns around and says, "Ha, Newton, I caught you." And Newton goes, "No, you didn't. I'm 1 Newton over a square meter. You caught Pascal." Like most physics humor, rarely laugh out loud kind of stuff. But inside, I'm sure you're all enjoying it inside. All right. Since the pressure being applied depends upon the depth of it, and it turns out anywhere along here is going to have the same pressure, anywhere along the same height. If you look at the simplistic formula here, it just depends upon, or I say height, depth. So the deeper you go, the more pressure there is. So if I take my cube there, there's obviously a force acting on the top because there's pressure from the water above it. And there's pressure coming from below it too. Now, the water from below is at a deeper level. Therefore, this is a greater force than this is. That difference is the buoyant force. All right, questions at this point? I'm about to sort of change gears. Now, the next bit really works a whole lot better if there's not a pandemic going on. So we're gonna have to use sort of theater of the mind. If I take a piece of paper, or something like that, if I blow across it, what's gonna happen?
It's gonna wiggle.
A little bit more detail. I'm not blowing off the edge, I'm blowing over top. Why is it gonna wiggle?
Cause paper's really thin.
Need more detail? Or are you just leaving that hanging for someone else to pick up? All right,
Air resistance. Air resistance.
which way does it wiggle? All right, so if it starts like this, it's gonna wiggle, which means it has to go one direction or another. I was gonna connect it to air resistance in just a moment, I did here. So as I blow across it, does it do this or does it do this? So you're gonna say it's gonna come up. Do you know why? It should. Now, the reason it's gonna wiggle is as you blow, one, it's very difficult to do a constant breath, but this should rise some as air flows across it. And air resistance typically would be, as this thing starts moving, the molecules are gonna hit it, which would cause some air resistance right there. It was a weak connection to air resistance, but there's a connection slightly there. What's happening is that the pressure on this side drops.